Hi Kayla, it's Elliot here. Just have a few minutes there and have a little chat about trig identities. And before we get started with the actual use of trig identities, I'd like to just review for a second about the unit circle. And I find that most people, when they get a chance to start this, or a lot of schools and teachers when they start this, they don't spend quite enough time explaining the unit circle and where things come from. So I want to take a second and just review that with you for a second and show how things get started, then show you how it turns into something that looks quite ominous, but it's not really that bad once you understand where the numbers and where the identities are coming from. So here we have a unit circle right here. Right here, you can see. So we know it's a unit circle because I took my ruler right here and I put it up here and measured the distance from the origin or the center of the circle to the edge of the circle. You can see that it's actually 1. So we measure it and it's 1. Great. So that's a unit circle. Now let's take our protractor and move it in here. And let's make it an angle inside the unit circle. Okay, so let's make an angle. Let's try 30 degrees. Alright, so let's make that angle 30 degrees. Put that out of the way. Let's bring this angle back in here right now. Have a look at it. Okay, so what I want to do now is actually draw a couple of lines right here. I'm going to draw this one from here up to here, and one from here to here. Now, if we look closely at those, we know very easily that this being our y-axis, this being our x-axis right here, we know that this piece right here will be our y, and this piece down here is going to be the x. So when we look at sine and cosine, for example, what does that actually mean? So if I have sine sine theta is actually equal to y over the radius. In this case, it's going to be y over 1. How do we know it's 1? Well, I took my ruler back here again, right here. And I put it back in here. And I moved it up. Oops. I'm going to set it this way. If I moved it up, you can see that when I measure it, it's still going to be 1. Cool? Nice. I'm just going to undo that. Get the marks out of the way. And put this back down here. So this is y over 1. Now we can also take this piece right here. This ruler is regular ruler because I can take this now and I can go like this. And on the side, like that. I can measure the side over here. You see if I measure the side right here. Wow. This is 1 up here. If I measure the side here, the y value turns out to be my pen. It turns out to be 0.5. If I took it back down here and had a look again, oops, down here, measured the x value, the x you can see would be, oops, 0.5678. It's not quite the 9 if I were to line up exactly right. So you see 0.9 is here, so 0.5, 0.6, 0.7, 0.8. It's a little past 0.8, but not quite to 0.9, which means the cosine, cosine theta is equal to dx over r, which is equal to x over 1, which is equal to 0.866. And I also want to make sure I point this out because this is really important. because it's the y over 1, all the sign means is the distance, no one ever tells you this, the distance from here to here, which is 0.5. You're like, what? So basically the sign value, the sign simply means the distance on the y-axis. No one ever tells you that, but just watch this. If we were to put a calculator up here, we would throw this over here and just turn this on. And I went sine of 30 degrees, you guessed it, 0.5. And for example, if I were to guess cosine 30 degrees, once again, it's just the distance along down here, and it's going to be 0.8660. So the cosine is basically the distance on your y-axis, or the value of y, and the cosine is the value of x. And that's all it is. Done. Pretty neat. Everything else comes from this point here. So if you're following along now, everything's good. Everything else actually comes or stems from this. So down here, if I were to take this, this actually equals my x-axis or value. Nice. Then they created something called tan. Tan basically is something that they invented just to make your life confusing. I'm just joking. Tan theta is going to be y over x. So, the thing about trigonometry in terms of identities, when you get this thing going on up here like this, I'm just going to maybe move this down a bit and just show you what I mean. When I have this thing here happening where I have sine, because it's sine theta y over 1, sine is my y, I can use this here. My sine of theta is actually just my y value. Down here the same thing goes. My cosine theta is actually my x. So when I see one of these like this, I can substitute. What I mean by that is that I can use this, or instead, if I want to, I could use this. Same down here, I can use this, and if I don't want to use cosine theta, I can use x. So down here, you'll notice this is where it gets starts getting kind of a little sneaky a little bit, because it says that tan is y over x. So what that means, if I use what I just mentioned up here, and instead of substituting, if I substituted sine theta instead of y, so if I used sine theta instead of y, down here this would turn into sine theta. The bottom, if I use cosine theta instead of x, would turn into cosine theta. Neat, eh? So that's where this piece here comes from in terms of the trig identities. Let's take it a little further. Let's take the trig identities and put it in terms of Pythagorean theorem. So, Pythagorean theorem says that if I take this side right here, y, and I squared it, and then the x side, and I squared that, and I have them together will be equal to this side here, which is the radius, squared. So basically what I'm saying to you, Pythagorean says, according to our little picture that we have drawn over here now, Pythagorean says that y squared plus x squared equals r squared, the radius squared. So looking back at our picture again, the radius is right here. We already measured it. It's 1. So we know that part. So coming back down here, let's fix this statement here. This is going to be 1 squared. if I up here I was saying how I can substitute y and sine interchangeably. So instead of having y down the bottom, I'm going to change it into a sine. So instead of using y squared, it's going to be sine squared theta. And instead of my x, I'm going to use cos squared theta. And then we'll keep taking it one more step further to the last step. It's going to be sine squared theta plus cosine squared theta, and 1 squared is equal to 1. Now, this one here is your has been derived, excuse me, from Pythagorean theorem. And this is probably the most important piece right here, because everything else pretty much comes from that. I'll explain what I mean by that in a couple of seconds. Before I do that, let's just have a look up here again. Let's start from what we know, but review what we know. So we have sine, cosine, and tan. So alright, so all I'm going to do, new page here. So I have sine x, sine theta equals y, and cosine theta equals x, and my tan theta is equal to y over x. Alright, let's take that and see how confusing we can actually make this. Before I move that, I want to move this over, just to give myself some little room here. Move them over a bit. And let's see if we can make this crazy, because it turns crazy, but if you can follow along, it makes sense after a bit. So these are our functions, or trig. So these are written as we mentioned a minute ago, because it's y over the radius. So basically, it's going to be what is this called? Y over 1, x over 1. So these are what's called the reciprocal identities right here. And reciprocal is a big word. I don't like using really big words in math. I try to keep it simple. So what that means is just take this one right here, flip it upside down, and you have the reciprocal. So we take that here and we go, oops, I'm big on colors, so I just want to get rid of that color. We go over here and we go, no, this eraser. Here we go. Alright, if we go here, we go 1 over y. 1 over y. Again, just taking this turn upside down. They've decided to call that cosecant. And they decided to put in a abbreviation for that. Back here we go. Let's see, C theta, and there you go. And then our secant equal to, let's see, C theta is, of course, as you know now, 1 over x. Just turning it upside down. And down here, our cotangent COT theta is going to be x over y. Now, it's all flowing nice and easy. All we're doing is taking this turned upside down, upside down, upside down. So now, what I'm going to do here now is take this, what we know, what we created right here, make it a little more challenging. Just rewrite it a little different way. What I'm going to do, just one second, I'm going to take this here. Oops. Oh, maybe not. What I want to do, I'm just going to start it over. Take this piece right here, all these pieces up here, and just rewrite them. So this is important. I want to show you how this looks. So, my cosecant here, CSC theta is equal to 1 over y. And we said back here that sine over y could be used interchangeably. So here, if my cosecant is 1 over y, then that's the same as saying 1 over sine theta. And if I use secant theta, it's equal to 1 over cosine theta. Oh, sorry, I moved it over here. Well, I need to have myself. 1 over x first. 1 over x, which is equal to 1 over cosine theta. And now that we have tan theta, sorry, cotan theta, which tan is normally y over x, this is going to be x over y, which is going to be cosine over sine theta. Now, summarizing this and removing the middle piece, you get a whole new set of rules that look like crazy things, but now that you see where they come from, is not so bad, because now we just see that cosecant CSC theta is equal to 1 over sine theta. We see that secant theta is equal to 1 over cosine theta, and we know that cotan theta is equal to cosine over sine. Now, hopefully that's all makes sense and you're following along right now and everything looks good. I'm going to show you now how you can take all you know here, and basically we're fully set up now to do pretty well everything you need to do when it comes to trigonometric identities. You're thinking, what? No way, I don't know anything yet. Well, let's just pop to the next page. What I did here, I cut out the page, you sent me that link. I cut out the page that your teacher was using, and I put it in here. Pretty cool, I can do that, hey? So, if you want to look closely at what your teacher said and what I said, and compare, you can see it's pretty much exactly the same thing. Right here, for example, I know it's a little harder to visualize the unit circle here, which is why I like doing it this way. And you see the unit circle, but it's still the same principle. And you see here how we had y over 1 and x over 1, and y and x equals sine and cosine. It's the same thing. Right here we have an x squared plus y squared equals 1, which is Pythagorean. And of course we know that this one's here. So what I want to take a second to show you this piece right here. It may be a little confusing. So that piece there comes from right here. I would just come up here. If I were to go sine squared theta plus cosine squared theta equals 1, I can do some algebra here. And I can take this piece. This behaves, each one of these, this one and this one, behaves as if it was a number. So basically, you can take this and you can move it over here, or whatever you want to do with it, as long as you treat it like a number. So if I were to do a little bit of algebra with this, I want to put the sign over here. It's going to look like this. My bad. Cosine squared theta equals 1 minus sine squared theta, which you see is right here. And it's all we did to take Pythagorean theorem and put some algebra behind it. And the same thing, it looks like we get two new equations, but we really don't. We're really still using the one equation, still using this equation and this equation only. And it looks really crazy when we get down here, but it's nothing different. Just root algebra applied to Pythagorean. And the same goes for sine. So we can have sine theta, sine squared theta equals 1 minus cosine squared theta. So now we have more rules. They're not really rules. They all came from Pythagorean theorem. Now, thinking about trig identities and solving them and proving them, you got to keep in mind is the substitution piece. Whenever you see this piece here now, you can substitute in this piece here because they're equal. Same down here, whenever you see this piece, you can sub this piece in instead, or vice versa. They're interchangeable, one or the other, because they're all equal, right? Okay, I'll let you think about that for a second, because maybe a bit out there, but if you have more questions on that, let's talk later. It's kind of like an equivalent fraction. For example, I could say something like this. 2 over 4 is equal to 4 over 8. So whichever one of these I use makes no difference because they're equal, they're the same, they're both equal to 0.5. So it's the same up here. They're both equal. I can use either one of those. So, and then before I move along forward, you can see right here where he mentions tan is y over x, and it's sine over cosine, and cotan is just taking this, turn it upside down, cosine over sine. So all of these here, basically down here, are these ones up here, upside down. All right, rock and roll. So then you say, okay, that's coming along good. Hopefully you're making sense to you now, and you're really starting to see what's happening. Then we get down to these bad boys down here. Oh no, you've got stars by them. When you see a star by them, that means either really pay attention to it, or it's really bad, really tough. But as you're going to see now, it's not going to be so bad, because what we're going to do, we're going to use these pieces that we talked about, substitute in what we know, and let's just see what happens. And hopefully what will happen, suddenly the lights will come on and you'll see how this works. So if I have the first one here, number 7, so I just take number 7, and I have cotan squared theta plus 1 equals secant squared theta, right? Okay, well, when you first see that, you're like, I don't even know what's going on here, but let's just take a look. Let's look more closely. What does cotan squared theta actually mean? All right. Well, cotan squared theta is actually this one over this one, cosine over sine. And before you can get moving further along with it, what I want to do, I want to put that over here. Take this and put it on that side over there. So it's going to look like this. We're going to have 1 equal to, this is just basic algebra, cosecant squared theta minus cotan squared theta. So let's look up here. Cosecant squared theta, cosecant being right here, it's actually 1 over sine. So let's change it up. Put down here 1. So this is going to be equal to 1 is equal to 1 over sine squared theta. So see what I did? Substituted this piece right here with this piece right here. It's the same thing. They both mean the same. Cosecant and 1 over sine. They're the same. How about cotan squared? Cotan's right here, which is cosine over sine. So my cotan squared, it's going to look like this. Minus cosine squared over sine squared. Now we're down to this part here, and basically what we have now are 2 fractions. If I were to take this out of the way, I love being able to do this. It's really neat to be able to do this. This software is fantastic. I love it. So now we have a fraction. We have 1 over sine squared theta, 1 over and cosine squared over sine squared theta. So the denominators or the bottoms of these fractions, they're already the same. So let's add them together. And what happens? Now the top becomes 1 minus cosine squared theta over sine squared theta, and that's equal to 1. Well, now we want to keep the sine squared in the denominator. Let's get rid of the sine squared, take it out of the denominator. And how do we do that? Well, we multiply both sides by sine squared, and watch what happens. So it's sine squared over this side. Sine squared times 1 gives me sine squared theta. On this side, I have 1 minus cosine squared theta over sine squared multiplied by sine squared. This should be starting to look something recognizable now. Sine squared theta will cancel sine squared theta. Now I have sine squared theta equals 1 minus cosine squared theta. And let's bring the cosine back on the other side, and you see I have sine squared theta plus cosine squared theta equals 1. And guess what? Look at this. We're back to Pythagorean theorem. That's all this is. This looks really nasty up here, where we started, but it's basically Pythagorean theorem rewritten in a messed up looking way. That's all it is. You're thinking, what? So this, we just took this, think about it, we just took this here and turned it back into this here. Crazy, eh? Well, it gets worse because this we can do it again for the other one we want to. Just to show you. Let's take the other one back. Versus 1 plus tan squared equals secant squared. Okay? So, what I want to do is take this 1 second. Up to the next page. There we go. Clean paper. Up here a little bit. So let's look at number 8 down here. You're thinking this is way out there. This one right here. So we have 1 plus tan squared. Sorry, 1 plus tan squared theta equals secant squared theta. Now, when you're doing these identities, it's really important that you can't forget some of these things right here. These you really got to know this stuff, or it's going to, you know, you memorize this stuff, or it's going to be complicated. This stuff you got to memorize here. You got to know this. You got to memorize this, and you got to know this one, and you got to know these. But basically, if you know that sine theta is y over 1, cosine theta is x over 1, and tan theta is y over x. Then you can take these and you can create these now from what you know. So if you want to minimize the memorization, this cosecant, this one upside down, turn this y back into a sine, and you got this formula here. This one, flip it upside down, turn the x back into cosine, you got that out there. So if you know this piece right here, basically you can find all these pieces down here. All right, so back to where we were going. I want to show you how to memorize these things because it's important. Because knowing these 1 over sine theta, 1 over cosine, all this stuff right here, it's kind of important because if you're trying to find a way to prove it, you've got to know how to substitute these together and how to change them around so that they work out fine. So tan squared theta, we know that tan squared is actually y over x, which is sine over cosine. So let's put it on here and just work this through. So this means we have 1 plus tan squared is going to be sine squared theta over cos squared theta. And secant up here, we notice, or in the notes, secant is 1 over cosine. So we have 1 over cosine squared. So secant squared is 1 over cosine squared. Notice how we're substituting, right? 1 over cosine squared theta. So all we're doing is that instead of writing down secant squared theta right here, we're inserting this piece right here, down here. See? So basically, instead of this, it's now this. Perfect. Hope you're following along. I'm trying to make this as painless as I can. So let's take some algebra. I want to show you something really neat that I can do with this thing here. What's this? Oops. I can take this, what I want to do using some algebra, I want to make it extremely simple looking. Oops. Using some algebra, and show you what I mean by moving it over there. I'm actually going to move it physically. I'll get rid of that one piece for a second. Put it back. I can actually take this and move it over here. But you know, if I move it over there, I change the sign, and it's minus. So that's what I'm talking about there when I say move it, apply some algebra. But let's apply some algebra and keep it simple and show the transition. What's going to look like now is going to look like this. It's going to look like 1 is equal to 1 over cosine squared theta minus sine squared theta over cosine squared theta. And once again, you'll notice the denominators or the bottoms are the same, so we can write it as one fraction. We have 1 minus sine squared theta over cosine squared theta equals 1. And then, well, we want to get rid of cosine in the bottom. Multiply both sides by cosine squared theta. So we get cosine squared theta over here. Over here I get 1 minus sine squared theta over cosine squared theta multiplied by cosine squared theta. And up here you notice that this cancels with this one. Now once again, now it should start looking incredibly familiar. 1 minus sine squared, that's not a negative there, I should get that out there in case it confuses you. Sine squared theta over, sorry, not over, not bad, equals to cosine squared theta. And of course, now rearranging using some bit of algebra, we get cosine. Oops. Yeah, that happens. My mind is not cosine squared theta plus sine squared theta. Now it should look incredibly similar, something you've already seen. And guess what? We're back here again. Same as we were right there with that one. Same as we were right here when we figured it out in the very beginning. Isn't that amazing? Who knew? It's all the same stuff, and it all comes back from the first page when we talked about the triangle, which is part of the unit circle, and it's the x and the y value, which is the sine and cosine. And that's it. That's the whole secret to doing this trig identity stuff. And there's not a lot to memorize, because once you memorize the first pieces right here, sine is y, cosine is x, or y over 1, x over 1. Tan is y over x. Then you're off to the races. That's it. That's really everything. Once you have those three pieces, you can make all of this up right here on the fly. If you forget how to do it, know what you're doing. If you don't memorize these cosecant, secants, and cotangents, you can actually make them up yourself because you know the first part. You can create these. They all come from the first stuff you did. Okay. What I'm going to try to do, I might just take a second and just have a look at the question, the example that he worked out for you, and maybe we'll do a little example, and then we'll pause from there. Just 1 second. So I just realized I'm actually throwing a lot at you in one video. This is now half an hour long. So I'm going to stop there for a second and let you soak that in. And what I'm going to do then is actually I'm going to do another little video for you, basically, and I want to talk about this stuff here. I want to talk about radian measure and what happens when you have like sine x on the bottom of a fraction that cannot equal 0. These are a couple of pieces that you might not really get until it's explained until you see it, and then we'll do an example from your homework or from whatever you send me in your link, and we'll take it from there. But right now I'll just pause it for there, and then I'll make another video shortly. All right, talk to you in a minute. Bye.